Okay, we are looking at the mean and variance of gamma distributions. So we've considered so many distributions, but how do we find the mean and the variance of gamma distribution? If you still remember, the density function of a gamma distribution is given as a function of x equal to 1 over beta raised to the power of alpha gamma alpha x raised to the power alpha minus 1 exponential minus x over beta. So here your x is greater than 0 and your alpha beta also greater than 0, so 0 otherwise. This is the density function of gamma distribution. We are interested in deriving the mean and variance of this distribution. You should still remember the mean of any distribution is given by this formula: expected value of x equal to, if you are dealing with a continuous distribution, this is continuous distribution, so it's going to be integral 0 minus infinity to plus infinity of x, function of x with respect to the x. So this f of x here is the density function of this distribution, which we are going to substitute here. So if you do that, so we are going to have integral, instead of writing from infinity this time around, so our x starts from 0, so 0 to, so it is not specified where it ends, so we are assuming it's to plus infinity of x times this function of x is our density function, which is 1 over beta raised to the power alpha gamma alpha, then times x raised to the power alpha minus 1 exponential minus x over beta with respect to what? To the x. So we are taking out beta raised to the power alpha and gamma alpha because they are the non-variables in this function. So we are taking this and this out. When we do that, we are going to have 1 over beta raised to the power alpha gamma alpha integral 0 to infinity of x times x raised to the power alpha minus 1 exponential minus x over beta with respect to what? To the x. So if you apply law of indices, this, we assume that if you apply law of indices, this 2, that is, this is also raised to the power 1. We take the common value, which is power at the common base x, then the power will be added plus alpha minus 1. So this will cancel this, left with x raised to the power alpha. So we are going to have 1 over beta raised to the power alpha gamma alpha integral 0 to infinity. So here we are putting x raised to the power alpha exponential minus x over beta, the x. So x is the variable which we are considering. This also contains x, so that is why we left this and we are integrating with the x. So there's no way, since our ambition is to estimate the mean, which is going to contain x as a variable, we are going to use transformation method. In order to transform this, we can let this power, everything here, we can say let y be equal to x over beta. So if y is x over beta, this will give us, if we make x subject to formula, we are going to have x equal to this times this, we have a beta y. Then we want to change everything here. Anywhere we see x now, we are replacing x by beta y. Then anywhere we see x over beta, we are replacing it by what? By y. Since we've changed this, we need to change this as well. And how do we do that? We differentiate x. We differentiate with respect to the y here. So we are going to have the x equal to beta dy. So we are differentiating the x with respect to the y. So we are done. What else? We just substitute this for this, and this for this. We simplify. So let's go there. So it means or implies that expected value of x, which is our equation here, which is our mean, is going to be 1 over beta raised to power alpha gamma alpha integral 0 to infinity. Here we are replacing it by this, which is beta y, all raised to power of alpha. Then exponential, instead of writing this, we are writing y minus y. Then instead of writing this, we are replacing it by this. So we have a beta dy. So from that place, we are going to have a expected value of x equal to 1 over beta raised to power alpha gamma alpha integral 0 to infinity. So this is product law. We are going to expand it. It's going to be beta alpha y raised to power alpha exponential minus y. So the beta dy. Let's take this and this. Let's take them out. So our y will not be the variable. We have a 1 over beta alpha gamma alpha. So when we take this out, beta alpha, we are taking this out as well. Beta, then integral 0 to infinity. Left is y raised to power of alpha exponential minus y, then dy. So everything here is a gamma function. So it's a gamma function. If you study what we treated in our class, so this is a gamma function. If you still remember gamma function, the fact remains that we are adding 1 to the power here. That is, if you have a integral 0 to infinity of let's say y, or let me use a raised to power of alpha, then exponential minus a, then the a. So this, we are adding 1 to this to put it in gamma form, so which is gamma alpha plus 1. So this is what this will change to. So if it is integral 0 to alpha e raised to the power of alpha minus 1 exponential minus a, the a. So this, when you add 1 to this, the minus will cancel, then we are left with ordinary alpha. So this will be alpha. So if what is here is alpha plus 1, then as a power here, we are going to have it as alpha plus 2. So that is just the logic. So this is gamma function. So we are using this fact now. We are using this fact to proceed our work. So how do we do that? So how do we do that? You agree with me now that everything here will now change to expected value of x will be 1 over beta alpha gamma alpha dot beta alpha dot beta. So everything here will turn to gamma, since we are adding 1, alpha plus 1. So that's it. So to reduce our load, let's cancel this cancel. We're going to have a beta over gamma alpha times this alpha plus 1. So from the gamma function as well, gamma function, we can reduce this power in order to cancel this. We want to reduce this just like a factorial. Like, let's say you have a 3 or you have a 9 factorial over 8 factorial. So to reduce this, in order to cancel this, we can equally write this as 9 times 8 and stop at 8 factorial, because there is factorial here, 8 factorial. So this can just cancel this and left with ordinary 9. So we want to find the way to cancel this gamma alpha. So in order to do that, we need to express this. So this will just give us a beta over gamma alpha times this. And how do we remove it? We are just subtracting 1. Here we are adding, but here we are subtracting. When you subtract 1 from this, it's going to give you alpha. Then you repeat this again. The equal answer you have here is what you have inside, like this. So this will now cancel this. We now have an alpha beta. Therefore, our mean, which is equal to expected value of x, is equal to alpha beta. So that is the mean of the gamma distribution. So we can also find the variance of a gamma distribution. So how do we do that? Let's look at how we can find the variance of a gamma distribution. Variance. If you recall the properties of variance, we were told that variance, which is equal to expected value of x squared, Emmanuel, or minus expected value of x, or is the power of us here rather. So this is the mean, which we just calculated. We are putting the value of this here and scaling it. But this is the sample second moment, second sample moment, this. So let's look at how we can find this. So if you find this, the answer we got, we put it here, we subtract this from it. That will be our variance. Let's find this sample, the second sample moment. So according to the distribution property as well, probability distribution, we were told that expected value of x squared will be equal to integral minus negative infinity to plus infinity of x squared function of x with respect to x. So what we are going to do now is we put, don't forget this is our distribution, the density function, and we are under the gamma distribution. So this will also be integral 0 to infinity x squared. So the function now will be 1 over beta raised to power alpha gamma alpha exponential minus x over beta. So the x, let's take this out as well. 1 over beta raised to power alpha gamma alpha integral 0 to infinity. So we have x minus raised to power alpha minus 1 here in our distribution. So these two, when we use law of indices, so this will surely, 1 will go, we'll have an x alpha plus 1 exponential minus x over beta the x. So we are still using a transformation method. We want to replace, we are still going to use the one we used for the first sample moment. So we are replacing everything here by beta. If you still remember, so this one is our beta. We said, so when we were calculating the mean the other time, we discovered that our y is equal to x over beta, which gives x to be beta y. So the x is given to be beta the y. So we are going to substitute everything here again, so that expected value of x squared will be equal to 1 over beta alpha gamma alpha integral 0 to infinity. So here we are going to have a beta y all raised to power alpha plus 1, then exponential. Instead of writing this, we are replacing it by this minus y. So our dx will be beta dy this time around. So we are taking this one will be 1 over beta raised to power alpha gamma alpha integral 0 to infinity. So when you expand this, you are going to have beta alpha plus 1 times this will take its own y alpha plus 1 exponential minus y dot beta dy. So let's take this and this outside. So we're going to have a 1 over beta alpha raised to power alpha gamma alpha. So when this comes out, we're having beta to power alpha plus 1. This also comes out, is going to be this integral 0 to infinity, left with y raised to power alpha plus 1 exponential minus y dy. So here we can also, we assume this is a gamma function which can change to what? According to that properties, this can change to gamma. We are adding 1 to this, going to be alpha plus 2. So here will be 1 over beta alpha, gamma alpha times when we split this. So this is the same thing as beta alpha times beta. That's for this. Then this one times beta. Then everything here we change to gamma alpha plus 2. So this will take care of this. We are going to expand this. Let's expand this value in order to cancel this gamma alpha. So from here, expected value of x squared will give us here we are left with 1 over gamma alpha. So this will be beta square. So when we this multiply this two. So whereas here we are going to, I told you we are removing 1. 1 from this will give us alpha plus 1. So we repeat the same thing again, alpha plus 1. We want to expand this in a way that this will cancel at last. So we need to further this also. So this is beta square gamma alpha dot alpha plus 1. So to further this, we remove 1 again. We are going to get alpha. So gamma alpha. You can see that this will take care of this. We now have alpha beta square into alpha plus 1. So that's our expected value of x squared, which is the second sample moment. So now we can easily substitute this to the variance now. The variance, which is expected value of x squared minus expected value of x all squared. So the answer for this is this, which is alpha beta square into alpha plus 1 minus, so this we've estimated this, then we got alpha beta, so we scale it. So we can open this bracket as well. This time this will give us alpha square beta square, then plus this time this will give us alpha beta square minus, so when you expand this to be alpha square beta square. So this will take care of this. Our final answer will now be alpha beta square. Can easily say that mean is equal to alpha beta, and the variance is equal to what? Alpha beta scale. So that is how to derive the mean and variance of a gamma distribution. So I remain formula or Isaac as my real name. So you can subscribe and also watch more videos on this distributions topic.